I'd like to talk about opto-mechanics and other nonlinear responses to photons. This work was done by my student Haowei Xu and the postdocs Hua Wang and Jian Zhou. So first, I'd like to talk about light-driven structural phase transitions driven by a dielectric constant contrast, and later an electronic phase transition in the Foucault theory. And then I'm going to talk about bulk photovoltaic nonlinear responses in topological materials, which have a giant response to IR and terahertz that could be used for photosensing. And finally, I'm going to generalize that bulk photovoltaic effect to spin current as well as static magnetization. So first of all, if you have a structural phase labeled by this order parameter that can be going from FCC to BCC, and this is without the illumination. Now under photons, you can have this linear term where P naught is the static polarization that depend on the reaction coordinate. And this gives you the ferroelectric effect. And also you can have a second order term due to the real part of the dielectric constant for a photon of a particular frequency at a certain reaction coordinate. Now, with the time average in thermodynamic, that first term average out. So what controls, if you don't have a permanent polarization, is this second order term. And say previously you have a ground state phase under illumination, you can change the energy landscape. And under sufficient strong illumination, the barrier can even vanishes. So for example, if we take a tin oxide monolayer, which have two tetragonal ferroelastic variants with a cubic saddle point, then under illumination, because in X direction, one variant has a bigger real dielectric function than the other at a near edge frequency, this can cause this barrierless transformation under a critical laser power that is very easily experimentally achievable. And you can also use polarization in another direction to toggle this variant, as well as to drive the ferroelectric polarization that's associated with this string. So this can also be used to two-layer hexagonal boron nitride, which can either have this AA prime stacking with a certain dielectric response, or it can be shift to 1/3 or 2/3 into this A prime B or AB prime in terms of this bilayer slippage. And as a function of this slippage, you have different dielectric constant profiles. And so we can, for example, have this ground state AA prime, but AB prime is a metastable state. Under an illumination of 4.3 electron volt, however, the AB prime can have bigger dielectric constant than the AA prime, and in which case you can actually toggle or transition to this AB prime. And we have actually solved kind of molecular dynamics equation of motion, and we can show that such domain transition can occur on the time scale of picoseconds, compared to in GST materials where it require melting and usually happens on nanoseconds or above. So you can use this to drive fast martensitic transformation and interlayer slippage, and use it as a kind of a memory device. If you use, instead of visible light, if you use a terahertz laser, then there will also be a phonon contribution to the dielectric response. And so the theory is, you're going to have this oscillating field, and then you're going to have the energy landscape being tilted in both directions, so get an average energy. And with this, we can toggle the topological phase transition of this moly ditelluride from 1T prime to 2H, which is actually a topological insulator. And you can also actually, by imposing a high frequency photon field, you can also use the Floquet theory, where you convert a time-dependent Hamiltonian to the electrons to an effective time-independent Hamiltonian, where this Hm is the mth fundamental frequency of your Hamiltonian, and this can be used to build an effective like a magnetic field in this time crystal. So, for example, if you take a three-dimensional topological insulator bismuth selenide, then the surfaces are gapless. But because there is no magnetic element, there is no breaking of time reversal symmetry. But when you turn on a circularly polarized light, that Floquet Van Vleck approximation will open up a gap, and you would have all the signatures of a quantum anomalous Hall insulator. And so on the 2D surfaces on the edges, we can show that you're going to have this quantized spin current. So to summarize, light can be used to trigger structural or electronic phase transitions. Now, if you look at dielectric response and you try to, for example, maximize it, then the general trick is you try to increase this conduction to valence band hopping. And this would require you to have a bigger wave function mixing, as well as a big joint density state to increase this linear dielectric response. And topological insulators are, topological materials generally are very suited for this. So if you have a material with, let's say, a chalcogen P band and the transition metal D band, then when you turn on, let's say, the spin orbit coupling to induce this back gap closure and then reopening, you will have some P character, chalcogen P character in the conduction band and some transition metal D character in the valence band. And you will greatly increase the wave function mixing after this reopening. And also by choosing the crystal structure judiciously, the reopening can actually result in this kind of Mexican hat band structure, where in addition to, instead of like a point, you actually get a ring of a huge joint density state. So this is what we plot in this transition dipole intraband, interband transition dipole. And in a normal insulator, it's just a point. But in a typical topological insulator, it's much bigger Barry curvature because of the bigger wave function mixing. But with Mexican hat band structure, you're going to have a bigger joint density state as well. And if we take tin selenide, which is a topological crystalline insulator with a Mexican band hat structure, then we see that it actually, in the linear photoconductivity, there is actually this peak from the calculations. And in the joint density state, there is this sharp rising edge, which is absent in normal insulators. And this peak was recently found experimentally in another material with Mexican band structure. And we sort of get published in about the same time. And traditional infrared detectors like the Mercat have a gain or a loss of about a few thousand per centimeter. But in our calculations, by going through all the topological crystals, we found that there are few with 1 or 2 order magnitude bigger optical gain or loss, and this would be a suitable material for infrared detection. Now, moving from a linear to a nonlinear response, in the ensuing sections, we're going to discuss this so-called bulk photovoltaic effect, where you have the second order response in a current, which is DC current. So you can generate DC current under an oscillating electric field. And this is advantageous compared to the traditional photovoltaics, where you're limited by the band gap as your upper voltage, and you're limited by these Shockley Queisser limits. The only requirement for BPVE is that you have to have a material without inversion or parity symmetry. And generally, the design rules is that number one, you need to have a strong breaking of the spatial or chemical inversion. And number two is a smaller band gap is preferred. And number three is that it's preferable to have this PD band inversion or topological character as shown here. When you have a non-topological to topological transition, there is a bigger jump in the second order photoconductivity. So we're taking this 1T prime structure, which is a known TI, topological insulator, and it actually have inversion symmetry in the traditional, let's say, moly tungsten ditelluride. But when the upper layer is one chalcogen like sulfur and the bottom layer is another chalcogen like tellurium, you chemically break the inversion symmetry. And this breaking is very significant. So when we look at the band gap, these are on the order of tens of milli-electron volts or several terahertz. And compared to traditional 2D materials, which have on the order of tens of this BPVE photoconductivity, for this genus 1T prime monolayer, it have two orders of magnitude bigger second order photoconductivity. So this can be used for terahertz photo detection. And also when, because of this big dependence on the topology, when we apply elastic strain, that can trigger a trivial to topological insulator transition, there is a drastic change in the sign of the photoconductivity. So this abrupt change of the sign is a fingerprint of a topological phase transition and can be used to diagonalize it. So the take-home message is generally topological materials can have very strong interband transitions and very big linear, nonlinear responses, especially if you design a big joint density state. And it's also going to have a large, so these are generally, we're just talking about charge currents, charge response. In the last section, I'm going to generalize this BPVE to spintronics and also to magnetism. So in the BPVE, you have this motion of electrons under an oscillating electric field. You have this DC current. But what about a spin current? So we have used the quadratic response theory in DFT, and a very important parameter in this calculation is actually this electronic relaxation time, which in this simplified treatment, we have taken uniformly to be 0.2 picosecond. And it's important because this is the arrow of time. It actually breaks time reversal symmetry weakly. And we can show that you can have quite different selection rules, this BSPV effect from the charge current BPVE effect. All you need is breaking of inversion symmetry. So if you have inversion symmetry, you're not going to have charge or a spin current. However, when you have breaking of inversion symmetry without magnetic elements, under a linearly polarized light, you're going to have this shift current, which is due to the difference in the electron center of mass is a transition dipole from the conduction band to the valence band. That you have a shift in the center of mass of the electrons. This effect is independent of that relaxation time. But you're also going to have this circular galvanostatic effect, which is so-called injection current. And this is a coherent excitation in K and minus K, in the Boolean zone, and you actually shift the occupation. You break the symmetry in the occupation of them, and so that actually is proportional to the electronic relaxation time. And so this is generated under a circularly polarized light. When you talk about the spin current, however, because spin is a pseudo vector that behaves differently under time reversal and also under inversion, it's almost completely opposite. Under a linearly polarized light, you're going to have the injection current, which is proportional to the relaxation time, and under circularly polarized light, you're going to have both shift and injection. And so we have this pretty different selection rule for the BSPV effect. And it also behaves very differently, the charge and spin current, when you have a mirror symmetry. So when we take molybdenum with a mirror symmetry in X, under this EX polarization, we're going to generate a spin up, spin V, spin current in the X direction. But we're going to have a charge current along the Y direction. That's constrained by the mirror symmetry. And then in a bulk three-dimensional material with inversion symmetry, then inside you're not going to have either spin or charge current because you have inversion symmetry, but the surface would break the inversion symmetry. However, there can still be residual double mirror symmetries on the surface in X and Y, and that would eliminate any possibility of a surface charge current. But you can still have a surface spin current, this surface spin photovoltaic effect. So that is a prediction that can be checked later experimentally. And finally, by triggering this spintronic response, we can also, and with this relaxation time, we can also build up a static magnetization. So there is this linear Edelstein effect in metals, which is if you apply a static electric field, you're going to have a electrical current, and that is given by the unequal occupation in basically K and minus K, and this can give you a static magnetization. So that's the linear Edelstein effect. But there is a quadratic Edelstein effect, and it doesn't require the system to be metallic. You can show that by doing the quadratic response theory, that you can induce a static magnetization, just like the previous discussions. And this contribution, this can have both electronic spin as well as electronic orbital angular momentum contributions. And in fact, in this, it's very different from the traditional magnetization, ground state magnetization, where usually the spin dominate and the orbital contribution very often is just like 10% of the total magnetization in the material because of the quenching of the crystal field quenching of the orbital angular momentum. Under light illumination, however, we show that for monolayer molybdenum which you have this mirror symmetry, you can have a z-directional ferromagnetic response, and the orbital contribution can be up to 25 times bigger than the spin contribution. This spin contribution is already multiplied by factor 25 for ease of visualization. And also, if you have a bilayer with a mirror symmetry in this AA stacking, the symmetry rules tells us that you are going to have this antiferromagnetic ordering where one layer have x directional magnetic moment and the bottom layer have the opposite. So even though net you don't have magnetization, but this can actually trigger a antiferromagnetic hidden ordering. And if, on the other hand, you have this AA prime stacking, where you do have the parity inversion symmetry, then under a linearly polarized light, we can have this ferromagnetic ordering. So there is a table of selection rules that you can look up. And finally, if you don't have mirror or inversion, then generally you're going to have ferromagnetic or some kind of staggered ordering. And this can be used for spintronics as well as to toggle the magnetic domains in materials by a strong enough light. So if you look at the response rate, this is Bohr magneton divided by the voltage over angstrom squared. So it's a pretty significant effect. So under pulse light, you can actually generate pretty large static magnetic field. So compared with previous literature, there is a known so-called inverse Faraday effect, where you generate magnetization under circularly polarized light. There is also an inverse Cotton-Moulton effect, which is in magnetic materials, you can generate magnetization under linearly polarized light. But what we predict is that you will have, even in a non-magnetic material and under linearly polarized light, you are going to generate magnetic structure globally as well as locally. And this could be used for memory applications. So this so-called bulk spin photovoltaic and the static magnetization can be generated as a quadratic optical response. So to summarize, I've talked about in the first part, a photon-driven structural phase transition driven by the dielectric constant contrast, as well as in the Floquet time crystal theory, we can use it to drive a quantum electronic phase transition to the quantum anomalous Hall effect on the surfaces of bismuth telluride. And in the second part, I talk about how to increase the linear nonlinear responses. And it was shown that generally by having a topological inversion, a band inversion, you can greatly increase the interband matrix element. And by crystal structure selection, you can also increase the joint density of state in the maximum hat band structure. And that can be used for IR or terahertz photo detection. And lastly, we generalized the effect here to spin and magnetism. And we show that you can have this giant change in the DC spin current. So this is the bulk spin photovoltaic, as well as a nonlinear magnetization effect, and which curiously, the orbital part can dominate over spin part. And the physics of that, we think, is a spin is a photocurrent which encounter the local chiral atomic structures, and that can generate a big magnetic response. So thank you for your attention. I'd like to answer any questions.